Hello, everyone. Thank you for joining us today for our webinar with Alexis Carpenter with Axe Nano, Controlled Release Injectable for Treatment of Low Permeability Zones. A few housekeeping items before we get started. We are recording this webinar and everyone is kept in listen-only mode. If you have questions, we encourage you to submit those throughout the presentation using the question pane in the GoToWebinar panel, or you can email us directly. If you submit questions through GoToWebinar, we'll receive a report with the question and your contact information to follow up directly after the webinar. If you're interested in receiving a PDF or recording of the presentation, please contact us. We encourage you to share that recording within your network. And at this time, I would like to take the opportunity to introduce our speaker, Alexis Carpenter. RemRx is distributed by Technology Development Group, LLC, and was developed by Axe Nano, LLC, through support from the Superfund Research Program and the National Science Foundation. Alexis Wells Carpenter, PhD, is a Chief Innovation Officer at Axe Nano, a clean tech venture studio that develops and scales environmental products and services. Dr. Carpenter's expertise is in the design and application of multifunctional materials for use in the environmental markets. Dr. Carpenter has a Bachelor of Science in Chemistry from Virginia Tech, a PhD in Organic Chemistry from UNC, and a postdoc in Environmental Engineering at Duke University. And at this time, I will go ahead and hand it over.
Great, thank you, Ashley. Let's get sharing. All right, are we good?
Yep, that looks perfect.
Okay, great. Good, thanks. Thank you, Ashley, for having me, and Carus for hosting us on this webinar. I'll clarify that I have a degree in inorganic chemistry only because organic chemistry is so intimidating to me. So yeah, thank you again for having me. I'm really excited to share today about our controlled release injectable formulation. Just to reiterate what Ashley mentioned, so Axe Nano is the Strategic Research and Development Division of Tri-Growth Partners. And this product, controlled release injectable, as well as our controlled release polymer pellets, are available commercially through our subsidiary Technology Development Group. So today I'm going to talk about our development work of our controlled release injectable. We have some new data to share. This is a collaboration between the folks at Axe Nano. As Ashley mentioned, it was supported by the Superfund Research Program, Small Business Innovative Research. And we've been really happy to work with our partners at Redox Tech for field deployment, as well as Eduardo Mendez and Mark Widdowson on some performance modeling. So what we'll go through today is I'm going to start with the whens and whys of in situ chemical oxidation, which is referred to as ISCO. Some people on the webinar might be very familiar with ISCO, but I wanted to really highlight when and why you might choose it, and some of the limitations of traditional ISCO methodologies, which allows us to highlight the advantages of our controlled release oxidants. I'll talk about the controlled release injectable and how it's made and used in the field. Then I'm going to touch on some laboratory testing that we've done, as well as some field testing, and then performance modeling capabilities that we have to demonstrate how you might expect this type of material to perform at your particular sites. So in situ chemical oxidation is a great option. Chemical oxidation has really fast reaction kinetics compared to some other things such as bioremediation. And the choice of when to use ISCO is driven not only by the types of contaminants that you have, but also the characteristics of your plume or your contaminant. So the chemical oxidation is certainly a contact sport. One of the key limitations is that you have to have really good interaction of your chemical oxidant with your contaminant, because the chemical oxidants are so reactive that they're going to react with both target and non-target species. So if you're dealing with NAPL, you could use ISCO, but it's quite challenging because the amount of chemical oxidants that you would have to get into the space to knock down all of those contaminants is quite high. Also, a lot of the chemistry occurs in the aqueous phase, so the oxidants have to be dissolved in order to really achieve their oxidative capacity. So when you're dealing with NAPLs, that's a bit harder to do. So ISCO is a good fit when you're dealing with dissolved contaminants. And if your concentration is high, it could be a good fit. But again, you'll have to keep in mind that you're going to use a lot of oxidants. If your concentrations are quite low, it could still be a good fit, but you're going to spend a good amount of money in your oxidant payload that may or may not end up being in contact with your contaminants. So it's really site, as this whole business is, it's all site specific, and the cost and the efficacy is driven by the oxidant demand being what are the target and non-target species that are going to consume your oxidant, and then what's the size of the plume, again, because it's really a contact sport, and so your radius of influence will be quite important. As I mentioned, some of the advantages are the rapid treatment. That's really the key advantage for chemical oxidation over some other options, is that you get really fast reaction kinetics from some hot radical species such as persulfate. You can use hydrogen peroxide and generate hydroxyl radicals, or as everyone's favorite, permanganate, since this is a Carus webinar. What's also nice about chemical oxidation is that you get complete destruction as possible. There's less of a chance of stalling at daughter products. And it can be used in tandem with some other approaches such as bioremediation. Some of the limitations I've already talked about, but it really go around the high cost for dilute plumes, the short oxidation lifetimes, and that non-selective reactivity that you get. To date, it's been limited effectiveness for low permeability zones, and then rebound is commonly observed. We'll get into one of the causes for rebound in a bit. But if we could address 3 of these limitations of prolonging the lifetime of our oxidant, allowing it to be better placed into low permeability zones, and really being able to address rebounding, then we could broaden the utility of ISCO. So this is a nice, very simple cartoon, but that describes the traditional ISCO methods. And here we're really talking about liquid phase oxidants. So in this case, your oxidants are dissolved in water and injected into the ground. And the 4-letter word for this process is rebounding. And what that means is that if you look at this cartoon, we've got time on the y-axis and contaminant on the y, where you have some level of contaminant concentration, you do your injection, everything looks great, and then when you go back out, your contaminant level has increased again. Let me get my highlighter. And then currently the method to address this is to do a repeat injection. And this is often unavoidable because your oxidant that you've done your injection is going to continue reacting with non-target species. And so the current method for addressing this is reinjections of the liquid or the powder oxidants into the subsurface. So what causes this? This is one of my favorite general chemistry principles is Le Chatelier's. And really it's the fact that the system is always trying to reach equilibrium. And so if you recall from the first or second slide, I talked about that a lot of the chemistry that's occurring with chemical oxidation is occurring in the dissolved phase. So you do an injection and your oxidant is reacting with your contaminant in the dissolved phase. That's where your monitoring comes in and you're measuring decreased concentrations. Then your oxidant is consumed. So we're kind of in this number 2 phase here. And then as your oxidant is completely consumed, either through reaction with your contaminant or non-target species, such as natural oxidant demand or things like that, then what happens is that the contaminant, these little red dots that were stuck on the solid particles, then desorb back into the dissolved phase. This could also happen not just from desorption from soil, but also dissolution from NAPL phases as well. So the best way to deal with it, as I said, is to do reinjections. And really the central hypothesis around this new technology or new product is if we can provide a sustained source of oxidant into the subsurface, then we can avoid that rebounding. So we will never change the fact that the contaminants are in this like constant flux of absorption and desorption. But what we could do is if we could make sure that there's always some contaminant present in that dissolved phase, then you wouldn't see the repeating increase of contaminant concentration in your groundwater monitoring. You would have oxidant there to do continual degradation. So that's really the central thesis around controlled release oxidation products. We're not the first people to have come up with controlled release oxidation. Controlled release has been around for a long time in the biomedical space, and there's been some slow or controlled release products used for remediation as well. Our products use a proprietary polymer matrix that allows for controlled release not only through dissolution but also degradation of the polymer. And really the key for this is that you get a more complete release of your oxidant, which is an expensive thing. So you want to make sure that you're getting the most bang for your buck. So how it works is if you imagine that the oxidants are these little purple stars, and then the polymer is this porous matrix around the oxidant. And as water flows through the matrix, then the oxidant is dissolved and flows out into the surrounding area. So it does require water flowing through the matrix in order for it to work. And so therefore it's really requires to be well submerged into the to groundwater for treatment. You might be familiar with our first product, which is controlled release pellets. These are 1/2-inch diameter pellets that are great for using in excavations or wide diameter borings or soil blending. What we can achieve with these pellets is 3 times the duration of oxidant release over time. I'm showing here oxidant release from the pellets. These are just in batch reactors. So when fully submerged in water, we're looking at the release of the loaded oxidant over time. And if we look at permanganate here, you get pretty much immediate dissolution. Whereas with the controlled release, you get a slower dissolution of your oxidant over time. And again, if your oxidant is still protected in that polymer, it's not going to react. So you're not going to get that inefficient consumption that leads to rebounding that we talked about on the previous slide. We also have these for persulfate, and we have a new product that we've done some pilot testing with percarbonate that is essentially a slow release hydrogen peroxide. I won't talk about, we do have some pilot studies for the CRPs, mostly with our persulfate product, and we're seeing our oldest site is about 3 years old, and we're still seeing persulfate release even after that initial deployment. So having persulfate persist in the subsurface for 2 years is pretty significant. Okay, there we go. Switch to my highlighters, so now I can advance slides. Okay, so the CRPs are great, but they're really limited in terms of how they can be used, and they're limited in their radius of influence that you can achieve. So we often heard from clients, these are great, but can you make this an injectable form? And that's the focus of this talk today, is our new injectable form, where we take our proprietary polymer and everyone's favorite oxidant. It could be permanganate. Right now, the one that we have commercially available is permanganate, though we are working on a persulfate injectable as well. And when these are mixed as a slurry and water, then the controlled release matrix forms in situ. So this gross looking goopy thing is our controlled release injectable after it's been injected into the subsurface. I'll start with some laboratory studies to demonstrate that the in situ formation of the CRI can in fact achieve the slow release that we've seen with the pelleted forms, and then I'll get into some field studies. So the objective of this first lab 1 study was to demonstrate sustained release, and here we're comparing to equal amounts of permanganate from just a crystalline permanganate. So we took permanganate in its solid form, loaded it onto this column at the same mass of oxidant as our CRI, and then we're flowing water through the columns and measuring permanganate in the effluent using spectrophotometry. So there's no contaminants present in this current set, but I'll tell you about an experiment where we did have PCE present. What we want to demonstrate here is just the longevity that we can achieve from the sustained release. So the green line is our CRI, and the teal line is the permanganate slurry. The x-axis is pore volume, so the amount of water that's flowing through these columns, dissolving the oxidants, and then they're coming out in the effluent. And we're measuring the permanganate concentration in the effluent. If you'll note, this is a log scale on the y-axis. The x-axis is not a log scale. So we really do see that nice, long, sustained release of oxidant at around 100 ppm for much, much longer than the slurry, which just makes sense, right? The salts are going to dissolve pretty quickly and be flushed through the column. So that's great, but nobody's treating clean water. So what happens when you have contaminants present? This is a demonstration of the CRI, again in a column study, with the water that's flowing through the column is from a PCE impacted site. We don't have a comparison for this directly with the permanganate slurry, but here we wanted to demonstrate that the controlled release matrix is stable, that polymer is stable even in the presence of relatively high PCE and then some of the degradation products as well. This column was run for 3 weeks. Samples were taken twice a week. The flow rate was 2 feet per day, and a total of almost 6 liters of site water was flowing through the column. There was 55 grams of CRI. CRI is between 70 to 80% permanganate. We can make that tunable based on what's the site characteristics that we need to achieve the specific control release for. And then we measured again permanganate in the effluent. And I'll note that this was done by a third-party laboratory. First, we're going to look at, I should have designed this slide better, but if you pay attention to the graph on the left first, here we're looking at concentration of permanganate in the effluent over time. So we have an initial really high release of permanganate, which is really because you have that kind of loosely held oxidant that's quickly dissolved, and then that stabilizes over time. This the timeline here, we have a good space in between where we didn't have any data points, but what we're seeing is that over the course of a couple of weeks, we have a sustained permanganate concentration of above 100 ppm, and then after that 5-week time frame, we're down to a couple 1 or 2 ppm. And then, I also wanted to comment that from time 0 to 20, this is when COCs were flowing through the system. Our product was being compared to some other amendments, and at this time they cut the experiment off, and because our CRI was still releasing, they went ahead and continued the column study, but just with regular tap water to see how long would the permanganate last for. And then on the right-hand side, we're looking at contaminant concentrations. So we have the baseline groundwater concentration. This is the concentrations that were measured from groundwater sampling at this site. So we have 530 ppb PCE. There's also some TCE and DCE present as well. So chlorinated ethylenes are really good contaminants to do permanganate oxidation of. And then on the middle column and the right-hand column, we have the contaminant concentration from the column study that was done in lab. So samples of groundwater were shipped to the lab, and then we have T0 for PCE, TCE, and DCE before flowing into the column, and then after the 21-day experiment, measuring the contaminants in the effluent after being exposed to the CRI. And so the targets of PCE and TCE and DCE were all non-detect at that point. And so this speaks to the ability of the controlled release to release a sustained amount of oxidant to overcome those ppb level of contaminants. And I don't have a picture to demonstrate, after the column was done, we took the CRI and did like a column dissection to look at it, and we didn't see a significant MnO2 Rhine formation on the CRI. We're really seeing nice even flow throughout the entire matrix so that you're getting near complete removal of the oxidant from the CRI. We still need to do some calculations to convert this data to percent release to confirm how much of it was released. All right, lab studies are great, but everyone's much more convinced and excited about field data. So I'll share two demonstrations of CRI in the field. Our first field study was done, Redox Tech did the injections for us. And this was done in March of 2021. 2 injections of 500 pounds each of CRI was injected. This was actually a former UST site, but it has since been cleaned. This is at North Carolina A&T's research farm, where we were able to go out and do, our first injection of CRI. We were able to do a lot of soil borings and determine the ROI for the injection, and to understand and confirm that the CRI formed that controlled release matrix after injection. Before I get there, I'll just comment that the CRI is prepared on site. So again, you would order permanganate and then order the proprietary polymer. Those two are shipped to the site, and then they are mixed and can be mixed into a chem grout system, the polymer and the oxidant together with some water, and then is injected using pneumatic fracturing. We did our injections, and I'll skip to this slide and then go back. I'll highlight this right-hand column here. This is the site map. So we did 2 injection points. So injection well 1 is here and injection well 2 is here. And then we did a series of soil borings. These purple and black circles are all around. And with those soil borings, we were able to see the presence of both the permanganate front, that sort of dissolved permanganate that traveled farther, as well as some nice seams of the CRI material. So here I'm showing on the left-hand side, these are beautiful permanganate purple soil cores that was farther out from the injection well. And then the seams of CRI that we found in the soil cores. And to confirm that, though it was quite obvious that this is CRI, because you don't find this type of material on the subsurface, we still wanted to confirm that we're getting that controlled release. So we took this sections of these soil cores, we put them in a mesh bag and looked at release of permanganate over time when placing them in fresh beakers of water. So imagine that you have a little mesh bag of the sections of these cores, we place it in clean water, we're measuring permanganate concentration, and then we take that bag out and put it in a fresh beaker of water and keep repeating that process. So what you can see is that the CRI did in fact form in situ, where there's no CRI. This is the permanganate front that we see. You get a much higher initial release of permanganate, and then it dies off over time. Whereas with the CRI, you have that more sustained oxidant over time. So this was repeated a good number of times, up to 300 hours of kind of soaking in new DI water. We've also been monitoring permanganate concentrations in our monitoring wells at this site. So again, the purple is the injection well. And then we have 3 monitoring wells at the site. Temp well 1 is the closest to a injection well. Monitoring well 2 is about 10 feet away from its closest injection point. And then temp well 2 is a good bit farther, and we've never gotten data from this well, so I think it's pretty disconnected from the injection area. So here I'm showing, this is a graph of distance from each of the nodes. And then on the left, we're showing permanganate concentration in groundwater over time. Time being T0 is when the injection occurred. So temp well 1 is the yellow line. And we saw sustained permanganate concentrations in groundwater up to about 250 days. Since then, that well has been dry, so we haven't been able to get any samples from that well. But we are still seeing sustained oxidant from monitoring well 2 with a pretty significant amount of permanganate. So we're at 270 or 600 ppm permanganate, even almost 700 days post injection. And while this site didn't have any contaminant present, we do know that these levels of permanganate are sufficient for treating 100 ppm level of chlorinated ethylenes. The second field study that I want to share with you today is a very contaminated site. So whereas our first field study we talked about was a clean site, this one has very high PCE concentrations. The goal here, this was a relatively well-characterized site. We wanted to do an injection between up gradient and down gradient permanent wells in the presence of high contaminant and confirm the stability of the CRI matrix even with these solvents present. Let's see what else. And then so here we're able to look at permanganate release over time as well as contaminant degradation. The approach was quite similar to the field study 1 that I just talked about. We used, again, Redox Tech did the injection with the slurry preparation and the chem grout. We had 2 injection points of 500 pounds of CRI each. We injected across a 10-foot injection interval. And we did some soil cores after the injection, and we've been doing quarterly groundwater monitoring for both oxidant and contaminant concentrations. This is a site map of the facility, and our pilot area is down here next to the settling pond in the, well, I'll get to the next slide where we talk about concentrations. Some of the wells that we were able to put in at this site were nested wells. And so this is a nice side view to kind of demonstrate where the injection interval is with relation to the screened intervals for these nested wells. Permanganate, high concentrations of permanganate are more dense than water. And so a lot of times what you'll see is you might see permanganate concentrations increase in the lower interval screened wells than the higher interval screened wells. On the right here is a site kind of to orient you where we are in terms of our injection, soil bores, and monitoring nodes. Again, the purple dots are where the injection occurred. The blue dots are monitoring wells, and the brown dots are where we did soil boring. So similar to field study 1, we were lucky in finding CRI in our soil pores. That's what is shown here. You see these nice, really dark purple seams of CRI, and this thick cross-linked material demonstrates that the slurry after injection did form the controlled release matrix. And while the injection interval was about 10 feet, we saw CRI show up across these soil cores, both through the injection interval as well as a little bit farther down as well. Here I'm showing a graph. I hope it's helpful. It's overlaying soil cores with the purple bands being where we observed CRI in those soil cores, and then they're positioned across an x-axis of distance from the injection well 1. So we want to demonstrate what we call primary and secondary radius of influence, where primary radius of influence is how far did the CRI go as a result of the pressurized injection, and then the secondary ROI is what's the radius that the oxidant is dissolving from that placed CRI. So we saw CRI show up about almost 6 feet out from the injection well at this site. These are permanganate concentrations. Again, plotting those monitoring nodes. So these are the labels for the monitoring wells that you can maybe squint very hard and see in the graph up here on the right. And then here I'm showing the distance of those monitoring nodes from the injection point. And then we're looking at permanganate concentration at 3 months, 6 months, 9 months, and 12 months from injection. And these are all ppm concentrations of permanganate, so certainly sufficient for knocking down ppb level of chlorinated ethylenes. Not surprisingly, we saw permanganate show up at the early time point, very close to the injection point. And we've seen some permanganate show up at later points farther away from the injection, up to 13 feet away. And then as time has gone on, those concentrations have gone down. So if we look at temp well 1, which is really smack dab in the middle of our 2 injection points, we're seeing permanganate concentrations even after a year of about 200 ppm from that well. We didn't have background data for that well because it was placed when we did the injection. We see permanganate show up initially in monitoring well 11S, which is the shallow interval of that nested monitoring well 11 at the initial time points. And then some of the farther away wells did see some permanganate. We've confirmed from the way the spectra looks that it is in fact permanganate that we're measuring, though it was quite low concentrations. And then the last step is to take the permanganate concentrations that we're seeing and overlay those with contaminant concentration. And in this very busy graph, what I'm showing is trying to show a correlation between permanganate concentration and PCE concentration. So on the left hand y-axis is permanganate concentration. That is plotted in the purple line. On the right hand y-axis is PCE concentration and ppb, and those are plotted in the yellow bars. And then each section of this graph corresponds to a monitoring well node. So this section is monitoring well 11S. This section is temporary well 01, and so on. And then these are placed with increasing distance from injection well 2. So MW11S is the closest to monitor to the injection point, and then TW01 is second farthest away, and so on. So what we're seeing now that we're about a year out from the injection is that 11S, which is about 5 feet from the injection node, is certainly within the injection ROI, and it looks to be within the secondary ROI of oxidant being released. We're pretty confident that the decreasing PCE that we're seeing is attributed to the presence of permanganate doing that oxidative degradation, since we've seen the permanganate present in this well as well. And then for temp well 1, which is a little bit farther away than MW11S, we also believe that this is within the secondary ROI of our CRI injection. We're seeing decreasing PCE, which we attribute to the presence of permanganate because we're seeing permanganate show up in that monitoring well. And then it looks like as you get farther out, the rest of our monitoring nodes are outside of the secondary radius of influence that we see. While we did see some permanganate show up in these wells, such as MW5S and 5I, we saw some spikes. We think that this is likely from that dissolved kind of front of dissolved permanganate that was able to travel farther, likely found some preferential flow paths. And the reason that we believe that this is true is because we're not seeing a downward trend in PCE like we are with the closer wells. So what this tells us is that while the CRI is sufficient for releasing permanganate for extended time, it's sufficient levels of permanganate for knocking down these pretty high concentrations of PCE. But the limitation for this technology, which is also the case for a lot of injection-based methods, is your radius of influence. We think that this demonstrates that CRI is a really good candidate for use as permeable reactive barriers, where you would want to have sustained levels of oxidant to treat a relatively sustained level of dissolved contaminant. So it's not a great fit for a source remediation, but could be a great fit for a PRB and plume treatment. Sugar time. Another thing that we've been working on is performance modeling, which really the goal of this is to be able to give clients confidence and some sort of prediction of how they might expect this material to work at their site. Without an abundance of pilot sites under our belt, it's nice to have this groundwater flow modeling to demonstrate how we might expect this to perform at a specific site with specific hydrogeology and contaminant concentrations and that kind of thing. So we've developed a proprietary model that is able to predict the rate of dissolution of our controlled release injectable, and it accounts for the mass of material that's placed in the subsurface at a certain time, and then how that mass changes over time as a result of consumption of the oxidant, as well as the kinetics of release of the oxidant out of the material. And so this model has been informed by empirical data that we've collected in the lab and in the field, and we continue to tune it and improve it as we have more and more field sites. We're able to model not only the oxidant release, but we can model oxidant dissolution and transport. We can also model oxidant consumption. And so we can give you a prediction, for what it's worth, of how you might anticipate your target constituents to go down over time. The way that this is set up, I'm going to show some data of using this performance model when applying the site characteristics of our field site 1. So this was at the North Carolina A&T farm. Again, we have our 2 injection nodes here, injection well 1 and injection well 2. And the purple line, the purple circle, is our kind of estimated radius of influence based on what we saw with the soil borings. And then the model is predicting permanganate concentrations over time at these various points. And we're comparing it to what we are actually measuring in the field. So we have data that has the tag of measured. This is data from the field. And then anything that says modeled after it is data that is produced from our performance model. The last thing that I'll comment on is that there's model, and then there's model plus and model minus, which is essentially a step in or a step out from the actual measured position. Let's see what else. Oh, the concentrations are predicted from if you were to have a screened monitoring well at that position with a screened well interval equal to the actual wells. So we're taking concentration over a screened interval. There is absolutely some uncertainty that exists, as in all models and in real life as well. But in this case, the uncertainty that exists is the extent of where the injection is. So we had to make some assumptions about, where the CRI is placed, how thick is that CRI seam, and how regular or irregular is the injection footprint for that CRI. All right, so I've broken this into the measured versus modeled data for temp well 1 and for monitoring well 2. So we'll look at temp well 1 first. And here again, we're looking at time on the x-axis and permanganate concentration on the y. Our actual real world data is in the dark blue line. And then the modeled data is in the peach and the green and the light blue. And their proximity to the actual measurement within TW1 is what differentiates those three. And what we see with our model is that we can really nicely predict the concentration of permanganate at the longer time intervals. So you can see pretty nice matchup at 100 days and over. What we aren't able to model well is that initial very high concentration of permanganate that you see a few days after injection. And really, we think that the fact that we see this in the field supports this like dissolved permanganate front that we think is occurring, where you do your injection, you have some of that dissolved oxidant that travels farther and faster than the CRI, and then the sustained release is what occurs as the oxidant is being released from that polymer matrix. When we look at monitoring well 2, we see a similar match for our modeled versus our measured permanganate concentration over time. And in this case, this monitoring well, we've been able to get more data from. We again see that initial higher concentration in the beginning that then levels out over time. So we're pretty excited about this model. And really the utility here is because this is a new product and we don't have a ton of field data, we hope that this is another thing that can help you to understand how this might be a good fit for your site or for you to take to your client and to demonstrate the utility of it. We can, I'm not showing it in these graphs, but we can use this model to predict longevity of just a liquid permanganate injection or a slurry injection as well. So if you wanted that comparison, we could certainly do that. In conclusion, I hope that what I've been able to convey today is this novel injectable controlled release oxidant, some of the benefits of it. I will say it is not a replacement for all of the chemical oxidant requirements for an injection. It's really would be an addition to. So instead of 2,000 pounds of oxidant, maybe you would do 1,000 pounds of liquid oxidant and then 1,000 pounds of CRI. So it's not there as a complete replacement of your total oxidant delivery, but as a dose of longer lasting oxidant. It's amenable to available injection methods. We have some idea about a primary ROI versus a secondary ROI that can be achieved. We're really excited about this sustained oxidant levels that we're seeing at sites 1 and 2. We've done some preliminary economic modeling that shows, although the material cost for this is more expensive than the oxidant alone, the ultimate cost savings comes in the sustained delivery and the decreased labor of not having to go out and do re-injections 3 or 4 or 5 times. And we are excited to work with new people, so would love to hear any questions that you all have about how this might be a good fit for your site. Want to pause and say thank you to our field testing partners at Redox Tech and AECOM, and then the support from their Superfund research program. This is part of our Axe Nano team. We're doing an axe throwing activity, which is great with our name of Axe Nano. And then I wanted to show what does it look like to work with us. So the commercially available form of the CRI is distributed by Technology Development Group under the RemRx brand name. And typically what we do is you would reach out and say, hey, I have this site. I'm interested in learning about RemRx. We would request some site data. We would do some calculations to determine what's the oxidant demand based on contaminant concentration and the size of your treatment area. Some predictions on oxidant demand for non-target species. And then we would come up with a couple of different options for you where you have different ratios of fast release and slow release. And then we're happy to perform this economic analysis for you to demonstrate if it's cost savings for you or not. So thank you for your time. Thank you to Carus for the platform of the webinar, and happy to answer any questions.
Okay, perfect. Thanks, Alexis. We do have a few questions that have come in. The first question, are you talking about dissolved oxidants? And I think this was on your controlled release injectable slide.
Mm-hmm. Dissolved oxidant. So the way that the CRI is formed is by mixing the solid materials together. So this bucket of your favorite oxidant, this would be the oxidant in solid form. And then it's mixed with the polymer, which is also in solid form. And that's mixed in water on site in the chem grout type scenario.
Okay, and then the next question that has come in, why was there acetone formation? And this was in, I think it was field study 2.
Study 2. Yeah, we see acetone showing up in both the column study. There's some acetone present in the baseline groundwater concentrations. And then it also forms as well. It could be an oxidation byproduct of reactivity with permanganate and the chlorinated ethylenes. And then we see it also in, was it in this? We are seeing it at this site with PCE as well, but I imagine they were alluding to that column study. It doesn't last very long because it's so water soluble. So it typically goes away pretty quickly.
Okay, and then the last question that's come in, how high is the loading capacity per frac or per volume of slurry?
Ooh, good question. I don't know per frac. When we do the injection, it is, let's see, so we did 500 pounds in each batch, and I want to say it was about 1,000 gallons per batch. So we want to have pretty high solids to liquids ratio when we're doing the injection.
Okay.
And then the how much can you load per like injection or fracture, I guess is kind of a dependence on the site. That's why we partner with Redox Tech, because I don't know that very well. But I imagine it would depend on how permeable is your area. We typically would do like an injection, and then we would back up 2 feet and then do another injection. So about 100 pounds per injection interval.
Okay, that's great. And it looks like those are all the questions that have come in so far. If anyone has additional questions, feel free to submit those or reach out via email and we can get back to you on that. Thank you, Alexis, for presenting today. That was great. And thank you everyone for joining. Have a great rest of your day.
Thank you very much.